that work, sorry, I'll start again. The idea that work is equal to a change in energy is the basis for the work energy theorem. So delta E, I can rewrite as our energy final minus our energy initial. And then I can just rearrange the equation. I can just add the initial energy to both sides. So the expression will look like this. Energy initial plus work equals energy final. And that is the work energy theorem. We say a system has energy if it can do some useful work. When I asked you guys yesterday what energy is, this is the definition that that we use to kind of determine whether energy exists in a system or not. So if useful work can be done, we say energy is present. Otherwise, we have no way of kind of quantifying if energy is even present. There are a bunch of different forms of energy you guys have looked at before. Kinetic energy, energy in a moving object. Potential energy, assuming that your object is some height above some surface. Work can be done. There's heat energy, energy stored in a hot object. Chemical energy stored within the bonds of chemical compounds. The classic example is food. Your body gets its energy from breaking the bonds that exist in the carbohydrates of food that you eat. So sometimes when we do work, we make things move. There's a proof here to find an expression for motion energy. You've got this, you know this already. The expression for kinetic energy that we're trying to find is what? Ke equals half mv squared. And here's where that comes from. The definition of work is equal to a force times a distance. I'm not sure. Did Morrison go through a proof with you where this comes from? Or did he just give it to you?
I don't.
Okay, well, let's go through it. Work equals a force times a distance. We also know, though, that F equals ma. So we can say that work is equal to ma times d. Work makes you mad. There are a couple different expressions for this piece here. We're going to look at this expression here. Vf squared equals Vi squared plus 2AD. Okay, so this AD piece here, we're going to connect it to Vf squared equals Vi squared plus 2AD. What we've got to do, though, first is a technique we'll call it a technique. That's what my physics professors always called it. But the technique is multiplying by 1. But you have to choose the right one to multiply by. And this technique gets used in physics proofs through all fields of physics. So it feels kind of cheatery. To get this 2 in here, to make this 2AD, we're going to multiply this by 2 times a half. We don't actually change anything. So all I've done is multiply by 1. Multiplying by 2 and multiplying by a half doesn't actually change anything. What that lets me do, though, is this. I can take this expression here, this 2AD piece, and turn this into work equals mass times a half. The 2AD becomes Vf squared minus Vi squared so work becomes equal to the change in kinetic energy, half mv final squared minus v initial squared. So that's part of the idea where this work energy theorem even comes from. And all it is just manipulating the math in the right way. Sorry? Well, what's 2 times a half? No, 2 times 1/2. It's 1. So what I did here is I multiplied this by 1. Because multiplying by 1 doesn't actually change the expression you have. You can multiply by 1 again and again and again and again. So the one that I picked was 2 times a half. By doing that, I could take this 2AD and turn it into VF squared minus VI squared, because that's going to be equal to 2AD. That leaves me this half M is left over, and the 2AD becomes VF squared minus VI squared. I substituted it in here. And this is a technique, the one that you multiply by will change again and again and again in all of these different formulations of proofs. But this is a technique, this is the first time likely that you've seen this technique, multiplying by 1 to blow up a formula like this. But if you take a physics degree, you take an engineering degree, this technique is going to show up all over the place. The one that you choose to multiply by is going to change all over the place. Sometimes the one that you choose to multiply by might be something like sine squared plus cos squared, because sine squared plus cos squared equals 1. For those of you who've taken pre-calc 12 and remember your trig identities, right? So it depends on which one you need to make this thing work nicely. And that just comes down to practice. I'm not going to do the proof for the next one, but you know potential energy. What's the expression for it? mgh. Mass times gravity times your height above some surface. This h, I'm not going to rewrite it. I'm just going to direct your attention to this. H is the height above a reference surface. You can pick whatever reference surface you want. Okay? This reference surface, for those, hopefully this is going to bring back some memories as we go through some examples, but this reference surface, you want to pick it to make your life as easy as humanly possible. Don't try and be a hero by picking something gross. Flip the page. So in general, when we do work, we can give an object both motion energy and height energy or potential energy. So we say that work done is equal to whatever potential energy an object has plus whatever kinetic energy it has, energy that we've given it. However, if the object already had some height or some motion, the work is just the work just changes the amount of energy that's present. So we get this guy here. I'll write it again. We've already written it once. Energy initial plus work equals energy final. The expression that ends up being really useful here is this guy here, kinetic energy initial plus potential energy initial plus whatever work is done is equal to kinetic energy final or plus potential energy final. That's what's changing there. That's the expression. Another blue sequence, I believe. And then depending on the situations, some of these might be 0, and then our life becomes a little bit easier. So to solve problems using the work energy theorem, the first thing you want to do every time is to draw a diagram. Everything we do, either using the diagram that's given for you or drawing your own diagram, is absolutely necessary. My physics professors always taught me, or always tried to teach us that to draw our picture and then to erase it and draw it bigger, because the pictures you draw are almost never going to be big enough the first time. Then you've got to decide which forms of energy are present in the initial and the final state, and then apply the work energy theorem to it. It's not overly complex. So much of this stuff is, once you analyze the situation and you apply the proper formula, the rest of the work itself is pretty trivial. So I have some situations here. All we're going to do is analyze the problem and set each one up. So if I've got a person doing work throwing a ball, we're given a picture already. If we're going to use the work energy theorem to figure out how much work the person does throwing a ball, where are we going to label our reference height? If this is the situation we have a person standing on the ground throwing a ball, and we want to use the work energy theorem to figure out how much work is done throwing a ball. The picture is given to us. You want to use the height off the ground. Okay, if I call this H equals 0. And then I do my work energy theorem. I've got my energy initial plus work equals energy final. If this is height equals 0, what kind of energy does my ball have at the beginning of the problem? Mr. DeVries, good morning. What's up? Oh, absolutely. I'll just keep going while he's doing that.
Yes, please.
What kind of energy does it have at the beginning? Sorry, Nathan? Potential energy. So I've got some initial potential energy. Why does it have initial potential energy? Because it's off the ground. You called the ground the height 0, thinking that was a good idea. So you're going to add work to this thing. How much work does it have at the end? Sorry, no. What kind of energy does it have at the end? It didn't have any kinetic energy at the beginning? Why? Because it was at rest, okay. So what kind of, as you said, it has kinetic energy at the end. Is that the only kind of energy this thing has? It still has potential. How is the potential energy at the end? How does that relate to the potential energy at the beginning? Yeah, get more specific. Look at how the picture is drawn. So potential energy initial and potential energy final, you're telling me, are the same. PE initial equals potential energy final. So was there a better choice for, yeah. Instead of calling this height 0, why couldn't I have called this height 0? Because if I call that height 0, my work energy formula changes. I got energy initial plus work equals energy final. What kind of energy does my object have at the beginning if I'm going to use this to be my reference height? There's nothing. So there's just whatever work is going to be done. What kind of energy does this thing have at the end if I choose this to be my height equals 0? Just kinetic. So by choosing a best reference height, you can make your life easier or harder. I mean, is this hard to, is this hard to do? No, but by adding extra terms in there, you're increasing your chance of screwing something up. This is really easy. There's one term on each side, okay? We cool with the idea of choosing a best reference height? Okay. I don't know if I need to go through the rest of these. These are relatively straightforward. We cool with the rest of either of these two? Just by looking at them, what you guys feel you can come up with the work energy theorem for both of these? Or does anyone want to see me do both of them? Let me do C? Okay, we can do C. Look, about a cyclist moving up a hill. If that's my diagram and we're wanting to find the work energy equation for it, we need to define a few things. We need to figure out what potential energy, what kinetic energy exists and where. So where do you want to call 0 for your height reference height? Sorry, Animal, did you say something? Oh, at this location here is where you want to call 0? Okay. So if I call that H equals 0, that means my potential energy equals 0 at that point. What else is 0 at this point? Kinetic energy equals 0 at this point because this thing's at rest. That gets rid of this term here. That just means I have work is equal to, what kind of energy exists at the end? This guy is now at some height h. So I've got potential energy at the end and kinetic energy at the end. He's still moving. This arrow implies that there is some unknown velocity. Your reference height can't change. Once you define a reference height, that's got to remain that for the entirety of the problem. So if my reference height here is the bottom of the hill, it's got to remain that. It's not the ground, it's a position on the ground. So like, even if like, you look, like if we're using this physical world as a reference, if I call the parking lot height 0, I have no potential energy, and I've walked upstairs here, in that system, I now have potential energy. But if you're looking at the problem with fresh eyes, and this is where you choose to start, you would say that I don't have potential energy here, but if I walk back down to the parking lot, my potential energy would have to then be negative. Because I'm going. And the idea of negative potential energy doesn't make sense, because it's not like I'm going to get flown up into the air by my negative potential energy. You've got to remain consistent throughout the entire scope of your problem. The implications of that get weird. Which we're going to see when we look at orbits, actually, but yeah.
This is kind of off from this, but relating to yesterday with the efficiency, wouldn't like a toaster or space heater be nearly 100% efficient?
Hey, what, sorry?
Like a toaster or a space heater, because they're both just producing heat energy. I don't know.
No, they're horribly inefficient.
But I thought the whole point was producing heat.
The amount of power they require to generate the heat that they do it doesn't correlate 1-to-1.
Oh, okay. Makes sense.
Okay, so Zach, Zach wanted to CC. Does this make sense? Okay, flip page. I've got D and E here. Do you want to see either of these, or do you feel like you could figure it out? See both? Okay, so I've got an elevator doing work lifting passengers. So again, the picture exists for us. This is what I want to play with, the work energy theorem, to figure out how much work is done. What am I going to call my reference height? The bottom of the lift. On the left, you said. So if that's h equals 0, then I've lifted this thing some height h. What kind of energy exists at the beginning? None. There's no energy at the beginning. Why is there no energy at the beginning? It's not off the ground and it's at rest. Okay? So because of this and this, energy initial equals 0. So that means some work was done to do what? What kind of energy exists at the end of the problem? Just potential. Why just potential? Because at the end it's at rest. So that tells me that KE finals at 0, but there is some potential energy. PE does not equal 0. So work in this case is just going to equal potential energy final. Same idea with the parachutist. Where do you want to call, or what do we want to call our 0 height, or our reference height, I should say it that way. What do we want to call our reference position in a situation like this? Sorry? This fully open parachute? Okay, so if that's my height equals 0, energy initial plus work equals energy final. What kind of energy existed? This is my initial situation. Some height above the ground, or some height above this level here. What kind of energy exists at the beginning? Kinetic and potential. PE initial plus KE initial plus some work being done is going to be equal to what? What energy exists at this level? It's just going to be kinetic. Why? This is going to be height 0, because this is what you've defined to be your reference height. Is this the ground?
But it's still your 0.
It's still our 0 because we focused our scope on just this part of the problem. The parachutist has however far to go to hit the ground. If you open your parachute at ground level, it's going to go bad for you. So the problem could theoretically still continue. But for the sake of focusing on this portion of the situation, we call this to be height 0. So at the end, there's just going to be some kinetic energy final. Sorry? Right there. Energy E equals Ke plus Pe, half mv squared plus mgh. This is the way it's formulated on your... that's not n minus c, it's n dash c. This expression right here stands for non-conservative. So, no, this is not a liberal at work. Okay? This just means that something is providing energy from outside your situation to change the energy that exists in your system. Because energy is always conserved. If you zoom out far enough, the conservation of energy is an important conservation law in physics. But to do this, like to slow our object down, some work had to be done to take energy away from our system, the system being the parachutist. So in this case, energy isn't conserved because it's not a direct relationship between the drop in potential and an increase in kinetic energy. Okay, so that's what that n-c means. I'll explain, this is a similar kind of thing, RT xi. I'll explain what that is when we get to gravity. But it's the same kind of idea. Okay, so let's apply this to this situation here. A cannonball, 5 kilogram cannonball is launched by a cannon. Sometime later, the cannonball is 8 meters off the ground and moving at 10 meters per second. We want to find the work done on the ball during the launch. There are 2 ways to approach this problem. This problem looks an awful lot like what other kind of problem? A projectile motion problem. So if this is a projectile motion problem, we could do what? Or we could use what? Kinematics is always an option. Okay? But I don't want to use kinematics, I'm going to use work to find the work done on the ball. So even the questions look similar, and we could use these techniques. We're going to choose to use energy. So I'm going to use my energy initial plus my work equals energy final. What part of the situation am I, I'm looking for the work done on the ball during the launch. What part of the situation am I concerned with? What am I trying to find here? What about during the launch? So if I take that a step further, what would that give me? Nope. This is the portion of the problem we're concerned with right here. Okay? So the ball was sitting in the chamber. Now the ball is ready to leave the chamber. The work done here is going to give this thing some muzzle velocity. The work to get the ball from where it is at rest in the chamber to out of the muzzle is what we're trying to find. So in this particular situation, what I am looking for, or what I could use this to find, is V initial at launch. And this is likely how the question will be posed. Like if I pose this question to you on a test or a final exam, say, I would give you that question, and I would say, what is the initial velocity of the projectile? If you want to use kinematics, what you could do is you could re-engineer this. You know this at some height or at some time, it's 8 meters above the ground, traveling at 10 meters per second. You could break this thing up into components. You could then work it, once you've got the x component and the y component, you could work it backwards because the x component's not going to change, and you could figure out what the velocity is of the ball as it leaves the barrel of the gun. Yes? Equivalently, you could use work energy to do the exact same thing. If I use work energy, this becomes a lot easier. What's my energy at the beginning of the problem? 0. Why? It's not moving. V equals 0. And why else is there no energy at the beginning of the problem? So you're defining this height here to be your h equals 0. Does it matter? Oh, yeah, actually it does. You're right. Sorry. I'm not redrawing it, but yes, it's where the ball is. So what I've got here then is just my work equals what kind of energy exists at the end of the problem? Kinetic energy final and potential energy final, because my thing's up somewhere in the air. So I'm going to have a half mv final squared plus mgh final. And I can just plug in my values. It's going to be a half. The mass of my object is 5. VF is 10. Plus 5 times 9.8 times 8. If you run that through, we're going to find that this thing has 642 joules of energy available to it. Relatively straightforward, yes? Comments, questions, concerns? Yes. This is the work required to launch the ball. Because here there was no energy. At this point, it has this much energy. The only way that it has this much energy at this point is if this much energy was put into the system at launch to get it to that point. Okay? Flip the page if you're cool with that. Oh, no, I have the page here. Okay, so I've got the same situation here twice. Okay? I've got a motor pulls a 250 kilogram mass up a frictionless 8-degree, 20-meter long ramp. The mass moves at a constant 1.75 meters per second. I want to find the work done. Okay? That's the way it would be posed to you on a test or final exam or whatever. Okay? This example says using work equals force times distance, and then they give you the same example down here at the bottom using the work energy equation. So the implication here is that we're going to see the same result using two different methods, and then later when you're just given a problem like this, you can choose how you want to solve it. So let's do it. If this is what we're told to use, what do I know about, or what do I have to do with my problem here? Sorry? Find the FG. Okay, so I'm free body diagram. Okay, so my free body diagram says I've got gravity acting straight down. So FG here is 250 times 9.8. What is it? No. What is that? $24.50. Okay. What other forces are acting on this object? No, those aren't forces, those are components. What other forces are acting on this thing? Normal. Normal always acts perpendicular to my surface, so it's going to be up at some angle here. And what other forces acting on this thing? We are told it is frictionless, which is nice. There's going to be, yeah, you can call it an applied force, you can call it tension, it doesn't really matter. I'm going to call this the applied force. If you want to call it tension, you're welcome to call it tension. So that's what we've got acting on this thing. Now, Nathan, if I want, well, I do want, this is where we break gravity up into components. So I'll have that guy there and this guy there. Remember, components always meet at 90. So that angle there is going to be the same as that angle there. That's 8 degrees. So my FG perpendicular is going to equal, I'm going to go back a step, 250 times 9.8 times the cosine of 8. The value you got for that, Zach, was what? 2426.2. And my FG parallel is going to equal 250 times 9.8 sine 8. Zach? 340.97. Okay. What else do we know? Okay, we know Fn equals Fg perpendicular, so that's going to have the same value, 2,426.2 newtons. What else do we know? Acceleration is 0. How do you know acceleration is 0? Constant speed implies acceleration equals 0, and if acceleration equals 0, what must be true? Sorry, one sec. Go again, Abigail. This has to equal Fg parallel because my acceleration equals 0. So you've got a value for that. That's 340.97 newtons. So to find the work done, using work equals force times distance, work equals Fd. My force is 340.97. Nathan, I think you said it earlier. What else do we need? Okay, or anybody else? We have distance. What's the distance? No, we've got the force. The distance is 20. We're given the length of the ramp here. Sorry, Nathan, you said earlier that we had to find the length of the ramp. We're given the length of the ramp in the problem. So I've got this. So we found that work is, if you multiply these things together, you should get 6,819.48 joules of work. Cool. Well, let's do it the other way. Can we use work equals FV? Work does not equal FV. Power equals FV. Power equals FV. Yeah. Why'd use the mass of the object in FG parallel? Well, 250 times 9.8. It's the same value. The reason I did that, I chose not to write it this way, but I could have written it like this. 250 times 9.8 sine 8 times 20 equals this. I could have used this formulation here. I chose not to do it this time, but now that you've asked about it, I'm going to write it down because you're going to see it show up again. This expression. Okay, so we've done it one way. Let's do the same problem another way. We're going to use the work energy theorem. The work energy theorem starts an entirely different way. It starts wanting this. Energy initial plus work equals energy final. When we're setting it up using the work energy theorem, what do I not need to do?
You don't need to do any of the components.
I don't need any of the components. I don't need a free body diagram.
So you have to do a little bit of work, just the ramp.
FBD is not necessary for the work energy theorem. You're right. I'm going to have to do a little bit of work with the trigonometry of the ramp, but that's relatively easy to do. So what do I need? What do I need to figure out here then? If I'm not doing a free body diagram labeling the forces on this thing, what do I need to label instead? Our reference height. Where do you want to call 0? The bottom of the ramp is what's going to make the most sense. So let's call that height equals 0. So then what do I need to figure out? I need this height here. Even easier than that. It doesn't have to be sine law. This is a 90-degree angle. And what do I know? The length of the ramp hasn't changed. It's still a 20-meter ramp. Because it's the same problem.
wondering now, measuring off the front corner of the box. We don't need to.
I mean, that's effectively the implication here. I don't need to necessarily make it more. I mean, the joules that it's going to change are minute. And yeah, if I were recreating this, the issue being having this thing hang off the end here is never going to be what it's going to be. Yes, you're not wrong, but we're going to ignore it the same way we ignore the mass and the ropes, and everything's going to be spherical. So what's the height? What's at the end? What height is our object at? Sine 8, and I'm going to leave it like that. And Blake, if we're going to get even more picky, it's not the height of the bottom left corner I should be concerned about, it's what height? The height of the center of mass. So this is actually the triangle we should be concerned with here. Okay, that's what we should be concerned with here. If we're going to get really technical. But because it's still going to be a 20-meter move at 8 degrees. Is the implication in the question. So at the beginning of my problem, energy initial is what? What kind of energy does my object have at the beginning? It has kinetic energy. This right here tells me that at the beginning I have kinetic energy plus some work being done is going to give me what kind of energy at the end? I'm going to have potential energy at the end, and I'm still going to have kinetic energy. So kinetic energy at the end. Okay, so I can put my expressions in here now. Kinetic energy initial is half mv initial squared plus work equals mgh final plus half mv final squared. Subscripts are important, include them. So now I can fill in my information. We know the mass of the object, right? Let's put it down here. The mass is 250 kilos. So this is going to be 1/2 times 250 times 1.75 squared plus work equals 250 times 9.8. My height at the end is 20 sine 8 plus my kinetic energy at the end is half 250 times my velocity hasn't changed. So before I ramp this thing through my calculator, is there anything I can do to make this thing nicer? No, before you ram this thing through your calculator, is there anything we can do to make this thing nicer? Well, these two terms are on opposite sides of the equal sign and they're exactly the same. Well, they matter. They cancel each other out. So you're going to get this expression for work. Work equals 250 times 9.8 times 20 sine 8. If I zoom this out a little bit, that same thing shows up here. Here, I used trigonometry to find this component of my force. Here I used the trigonometry to find the height of my ramp, but the same expression shows up in both locations. Sorry?
What's the reason for not
I just told you. To show you that using work equals force times distance and work equals change in energy gives you the same mathematical expression. It's mathematically equivalent, so it's procedurally equivalent. That might not seem like a big deal, but in physics, that's an earth-shattering realization that you can solve the same problem two different ways. In some cases, one of these will be the better option, an easier option. So if you can find an equivalent solution using an easier technique, that's something you want to hold on to. For those of you who are in calculus, this is the same thing as what you're going to look at. Is it today's lesson, Crystal? When is integration by substitution a thing?
Oh.
What? Boo. Okay, never mind. Okay, but that's an important, Nathan, that's why I didn't create an exact value here. To show you that procedurally these are equivalent. Okay? And we could get a value here if you round this through your calculator. It's the same expression here, so the work should be the same. 6,819.48 joules. Because if I would just have left you to your own devices, you would see, oh, the final answer is the same. Well, isn't that cool? But more importantly, the expressions show up in the same spot. That's the realization I wanted you to have. So the implication here, the reason we do this example is to show you that work equals force times distance is equivalent to using work equals change in energy. And the implication there, flip the page, is that these two situations are equivalent. Okay? Because, yeah, it looks like different drawings. But looking at the work energy theorem, if I use energy initial plus work equals energy final, does it care what happens in the middle? Okay? This thing here is path, the language here we use is this thing is path independent. So it doesn't matter what happens in the middle. All we care about is the beginning and the end. Because you've got energy initial, energy final. It doesn't say energy middle. Who cares about energy middle? Because they started at the same spot and they ended in the same spot, the same amount of work has to be done. Which we could take this a step further, and what happens if we throw a loop in there? Nothing changes. The implication is exactly the same if I throw a loop in there, if it's a straight slope or if it's a curved slope. Yes, it could slide back and forth as many times as we want, as long as it starts and ends in the same spot. The same amount of work will be done over the system that is the entirety of the problem. I'll let you guys play with this thing. Flip the page again. This lesson's relatively short. I feel like it's been going on for a long time, but it hasn't. I want you guys to look at these problems. Give you some time to play with these. 1, 2, 4, 6, 10, and 11. You want 3? You want me to give you 3?
Still hating on 3.
I mean, 3 is an interesting question. You know what? Fine. Let's give you 3. Yeah, 3. 3 is a good question. 3 is a good question. Okay. 3 is a good question. 1, 2, 3, 4, 6, 10, and 11. We'll give you some time to play with that. And then we'll move on. Good luck.